These next examples, they give us the ratio, but we're missing the angle. Notice the instructions say find all values of theta such that theta is between 0 and 360 degrees. That implies that there may be, in fact, more than one solution, and it turns out there will be, in most cases, two solutions. That's because, if you think about it, sine is both positive and negative in two quadrants. So let's think here. When is sine theta negative root 3 over 2? Well, the first thing we know, you cannot have an answer in quadrant 1, nor can you have an answer in quadrant 2, because quadrant 1 and 2 are both positive signs, and we want a negative sign. So therefore, our answers, our triangles, have to be in quadrant 4 or have to be in quadrant 3. So these are our two places that we're going to look for answers here. Now also remember, sine is the y value. So it's giving us the y side. It's saying the y side is negative root 3 over 2. So let's fill that information in. So I know my y values are negative root 3 over 2. Root 3 over 2, that reminds me of our special triangles. Opposite the root 3 over 2 is the 60. So we know those reference angles are 60 degrees. Now my answer's not 60 because that's not how we calculate angles. We always calculate angles starting from the initial side. So we go from the initial side to that blue terminal side I drew. So we know halfway is 180. So to get my first answer, it's simply going to be 180 plus an additional 60. Or in other words, 240 degrees. So 180 plus 60. That's one of my answers, 240 degrees, but I have another triangle over here that also is the same ratio. So I have to find this one. Well, I'm going to kind of think about it another way. All the way around is 360, but I'm not going all the way around. I'm 60 shy of going all the way around. So 360 minus 60 gives me 300. So for A, my two answers are both 240 degrees and 300 degrees. B takes a little more reasoning too, but I can start with the same principle. Cotangent, 1. That's the same as saying tangent is 1 because the reciprocal of 1 is 1. Where is the tangent positive? Well, the tangent is positive in quadrants 1 and 3. So because of this, I can rule out quadrants 2 because tangent is negative and quadrants 4 because tangent is negative. So my two possible answers must be residing in quadrant 1 or in quadrant 3. Now here's where we have to do some tricky math here. 1, it sounds like the answer is going to fall on the x-axis, and it would be true if we're talking about sine or cosine here. But tangent is the relationship between y and x, the two legs. When would the relationship between the two legs be 1? Well, in order for that to happen, both legs would have to have the same length. In order for both legs to have the same length, we would have to be talking about an isosceles triangle. And there's only one right isosceles triangle, the 45, 45, 90 triangle. So we know those angles are 45. And as you practice these, you'll start making these connections and seeing the same numbers repeat themselves over and over again. You almost get to a point where you memorize them. So we have two answers. Our first answer, in fact, is going to be 45 because this angle in the first quadrant from 0 to that angle is simply 45. And then my answer in quadrant 3 would be 180 plus 45 or 225 degrees. Remember, when we calculate angles, we always start from that initial side. Don't give me the reference angle. I know you need to give me the actual answer. Let's try one more here. Secant of negative 1. Well, secant's not good. I don't like secant. Let's think about its reciprocal. What's the reciprocal of secant? Cosine. So cosine of theta. And what's the reciprocal of negative 1? Well, it's negative 1. So when is cosine theta equal to negative 1? Well, here's where we have to use that same kind of logic skill. Let's look at our unit circle here, guys. So cosine of theta is -1. Remember, cosine is the x distance. Because the cosine is -1, I know it has to be on an x-axis, when in fact is the only time the x-axis is -1. Well, if I'm here, this is +1 on the unit circle, so -1 has to be going that way. So my answer here is going to be 180 degrees. And because my answer this time lies on the x-axis, I only have one answer. So whenever you have an answer that lies on an axis, you'll only get one answer. So we get 180 degrees. Okay. So those are the work you're going to be doing in a circle. And again, the more practice you get, the faster you'll get at it, and you'll realize these patterns repeat themselves over and over and over again. Even as it looks like I'm solving them on the unit circle, I'm doing this more from memory and pattern recognition than I am actually from solving. So let's look at some rules here. Let's talk about some domain and range for sine and cosine. We're going to need this in our next section. So the domain for sine is all real numbers. The range for sine, however, is from -1 to 1, meaning the highest value sine can be is 1, and the lowest value sine can be is -1, and both of these points occur on the actual axes. For cosine, it's the same thing. The domain of cosine is all real numbers. And again, the cosine values varies between -1 at its lowest and 1 at the highest. And once again, cosine hits both of these values on the axes. So if you're ever asked to find an angle that gives you a sine or cosine larger than 1, it can't be done. A periodic function. Let's read this first. So a function is periodic if there exists a positive number c such that f of t plus c equals f of t for all t in the domain of f. The smallest number c for which f is periodic is called the period of f. What that means: if a function repeats itself again and again and again and again and again, we call it periodic. The smallest interval on which it is unique is the actual period. Both sine and cosine are periodic, because think about it, they're both based on the unit circle. So every time you go around the unit circle, it repeats itself again and again and again and again and again, forever and ever and ever and ever and ever. And we'll see this when we graph them. So the period of sine and cosine is both one journey around the unit circle, which would be 2 pi. Even and odd trigonometric functions. We talked about even and odd functions. Remember, we defined an even function. If you have f of -x, it equals f of x. We talked about an odd function. If you have f of -x, it equals -f of x. So, turns out cosine and secant are even functions. I like to think of even functions as very hungry functions. They eat the negative sign. So cosine of -t is simply equal to cosine of t. Secant of -t is equal simply to secant of t. They just devour the negative sign. Sine, cosecant, tangent, and cotangent are all odd functions. That means the negative sign plops right out. So sine of -t is simply the same thing as negative sine of t. Tangent of -t is simply saying the same thing as negative tangent t. Cosecant of -t is the same thing as saying negative cosecant of t. And finally, cotangent of -t is equal to negative cotangent of t. Two last things to talk about here very simply, and we'll go over these theorems in much more detail in later sections. Because tangent, if you think about it, is equal to opposite over adjacent. And sine is equal to opposite, and cosine is equal to adjacent, then tangent is equal to sine over cosine. Because cotangent is the reciprocal of tangent, cotangent would be equal to cosine over sine. So these are our quotient identities. The last three identities we have are the Pythagorean identities. Sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared. And 1 plus cotangent squared equals cosecant squared. We will be seeing these in much detail in later sections, but I just wanted to give you guys a little preview before we end things today. So that will do it for the unit circle. Up next, we'll have graphing sine.